Welcome back. We continue our study of chapter 3 and we move to section 3.3 about compact subsets of Rn. So let us first start with the result that I mentioned in the introduction, that any closed interval of the form AB of R is compact. So we have to prove that by going back to the definition, or by using lemma 3.2. So we consider a covering of AB by open subsets of R, and we want to extract from this covering a finite subcovering. So we proceed in 4 steps. In the first step, we show that if X is between AB, strictly less than B, but bigger or equal than A, could be equal to A, then we can find Y strictly bigger than X, but less or equal than B, such that the closed interval xy is covered by exactly one element, or it's contained in one element only. Okay, so take an element x between A and B. Therefore, x belongs to the union because the union contains the interval. So therefore, x belongs to one of these sets. Call it OMU. So x belongs to OMU. But since OMU is open and x is an OMU, then we can find an interval, an open interval of center x, or a ball if you like, contained in OMU. This is the definition of an open set. Okay, and now take epsilon to be the smallest between the numbers b minus x and r. Okay, you'll see why I need to choose epsilon in this way. So first reason, if epsilon is less or equal than r, then x minus epsilon, x plus epsilon is contained in this interval x minus r, x plus r. Okay, and now choose an element y strictly between x and x plus epsilon. Now the assumption that epsilon is less or equal than b minus x means that x plus epsilon is less or equal than b. Then actually y is less than b. Okay, can make it open here. And therefore, the closed interval xy is contained in x plus epsilon, and so it's contained in x minus r, x plus r, and therefore it's contained in and that's it. So this completes the first step. So we found one element of the covering containing the closed interval xy. Okay, second step, we consider the set capital C of all numbers of the y in AB, strictly bigger than A and less or equal than B, such that the closed interval AY can be covered by finitely many O lambda. Okay, so the target now is to prove that C is not empty. C is bounded from above, so it has a supremum, and the supremum belongs to C, and then the supremum is equal to B, and then we are done. Okay, so let us proceed step by step. So in this step, so first of all, C is not empty. Why? Because it contains A. Okay, this is so if I apply step 1 to x equal A, which I can do, then I can find an element y such that AY is covered by one element, so by finitely many elements. Therefore, C is not empty. And by definition, C is contained in AB, so it's bounded from above by B. So it has a supremum. Okay, denote the supremum by small c. Okay, so now I will prove two things: that small c belongs to capital C, and then C equal to B, and we are done. So let us prove now that small c, the supremum of C, actually belongs to C. Okay, now C is in the interval AB, which is in the union. So C is in the union, therefore it belongs to one of these elements, O lambda. I call it OK. So C belongs to OK. And once again, since OK is open, then there exists an interval of center C and radius delta totally contained in OK. Now, by a fundamental property of the supremum, C minus delta is not an upper bound. So we can find an element Z in C, which is strictly bigger than C minus delta. And since Z is in C, then it's necessarily less or equal than C. Therefore, the interval ZC is contained in C minus delta, C plus delta, so it's contained in OK. Okay? So ZC is covered by one element. But since Z is in C, by definition of C, the closed interval AZ can be covered by finitely many O lambda. Therefore, when I take the union, so AZ union AC, which is AC, is covered by also finitely many elements, because AZ is covered by finite by, let us say, n elements, and ZC is covered by one element. So the union is covered by n plus one elements. And that, by definition of C, small c belongs to capital C. And lastly, I will prove that C is equal to B, and then we are done, because then if C equal to B, then by definition of capital C, the closed interval AB can be covered by finitely many elements of the covering, and then we are done. So we reason by contradiction. Of course, we know that C is less or equal than B. So suppose that C is strictly less than B, and I apply now step 1 to x equals C. So we find accordingly a point y between C and B such that Cy can be covered by one element. Let us call it oj. Therefore, exactly as we did in step 3, the interval ay can be written as AC union Cy. And now AC is covered by finitely many elements according to step 3, and Cy is covered by one element, so the union is covered by also finitely many elements. And therefore, y belongs to capital C. Okay, but therefore it should be less or equal than C. Okay, but it's a contradiction because y is strictly bigger than C. So therefore, C cannot be strictly less than B, and therefore C equal to B, and therefore B belongs to capital C, and therefore the closed interval AB can be covered by finitely many elements of the covering. And that's it. So this concludes the proof. Therefore, any closed interval AB of the real line is compact according to our definition. Okay, now I will talk about compact subsets of Rn. Recall that in Rn we defined three topologically equivalent distances: ρ1, which is the sum distance, the Euclidean distance that you know, and the square distance or the infinity distance that we considered in chapter 1. And we proved that all these distances are topologically equivalent. So it doesn't matter which distance you take. Okay. Now, and we also observed something very important, that these distances are related by these inequalities. So rho infinity is less than rho2, and rho2 is less than radical n rho infinity, and rho infinity less than rho1, rho1 less than n rho infinity. So actually, this is how we prove that they are topologically equivalent. But actually, we need more than just topological equivalence, because now when I say that a subset is bounded, I need to precise with respect to which distance it's bounded, because I will give a counterexample now. These inequalities tell me that if a set is bounded for ρ2, then it's bounded for rho infinity. And if it's bounded for rho infinity, it's bounded for ρ2. And same thing for ρ1 and rho infinity. So boundedness is also equivalent here in this case. Okay, so when I just say that a subset of Rn is bounded, it means that it's bounded with respect to any one of these distances. Okay. So bounded, as you said, you have several characterization of boundedness. So boundedness means that the diameter is finite or that it's contained in a ball. Same thing. Okay. And now I can state an elementary result about compact subsets of Rn. So how do I know that a subset of Rn is compact? A subset of Rn is compact if and only if it is closed and bounded with respect to any one of the usual distances. Okay, the Euclidean distance, if you like. Okay, so we have two implications. One implication was done in a previous section, because we know that if A is compact, then A is closed by proposition 3.3, because Rn is a metric space, and by proposition 3.4 it's also bounded. So compact in a metric space in general, not necessarily in Rn, in any metric space, a compact set is both closed and bounded. Now the converse is more interesting. So suppose that A is closed and bounded, let us say for rho infinity. Okay, so this means that A is contained in the ball, in the closed ball of center 0 and radius m. Okay, so the distance between 0 and x and the square distance is less or equal than m. But what does it mean that rho infinity of 0x is less than m? It means that the maximum between xi and 0 is less or equal than m. So each component of x is less or equal than m, which means that xi is between minus m and capital M. Okay, so A is contained in the square minus m to the power n. It's a square. But according to the previous theorem, minus mm closed is compact. And we proved earlier that a product of compact metric spaces is compact. So A is contained in a compact set, and since it's itself closed, it is compact as well. Because the closed of a compact is compact. And that's it. And now let me end with an important remark that why do we need to precise which distance we are talking about, because boundedness, unlike compactness, is not a topological property. So compactness is a topological property. So when you replace the distance by an equivalent distance, the compactness is the same. But boundedness, we may lose boundedness. For example, take the usual distance on R, d, and take d prime to be the minimum between 1 and the usual distance. Okay, we know that this is a distance and it's topologically equivalent to the usual distance. Okay. However, R is unbounded for d, for the usual distance, but it's bounded for d prime because d prime is always less or equal than 1. Okay. So therefore, R is closed and bounded for d prime, but it's not compact for d prime because it's not compact for d. Okay. So, okay. So this is why we should precise when we talk about boundedness. We need to precise with respect to which distance we are talking about. Okay. So, yeah. So let us give some fundamental examples. The unit sphere in Rn. So the unit sphere is just the set of n tuples x1, xn, whose sum of the square is equal to 1. Okay, this is the sphere of dimension n minus 1. And the closed ball Bn is just the set of points whose square distance, so the sum of the square is less or equal than 1. Okay, so here we can take, for example, the Euclidean distance. Okay, so these two sets are bounded, of course, and they are closed, as you know. Okay, there are several ways to prove they are closed, actually. We proved that a closed ball is a closed set. And the sphere as a closed set actually is an interesting result because we have several ways to prove that the sphere is closed. One way is to write it as the inverse image under a continuous map of a closed set. Okay, so this is a good exercise to check that the unit sphere is closed. Okay, but yeah. So this is the first example. So the unit sphere and the unit ball are compact. Now, if you consider part of the hyperbola x1 over x between 0 and 1, this set actually is closed in R2. And we proved something similar actually for x1 over x for x positive, okay, by sequences. It's not difficult to prove that this set is also closed. However, as x tends to 0, 1 over x tends to infinity, so this means that A is unbounded. So this set is not compact. Okay, a more interesting set. The graph of sine 1 over x for x between 0 and 1. This set is bounded because x is bounded and sine x is bounded between 0 and 1, and sine x is bounded between minus 1 and 1. So S is contained in a square, so it's bounded. However, it's not compact because it's not closed. Okay, why it's not closed? You tell me. We have to find a sequence in S converging to a point not in S. Okay, and as a challenging exercise, find the closure of S. What is it exactly? We'll get back to this important example in the next chapter. Okay, so now we have a very simple criterion to detect compact subsets of Rn. It's very easy. So it's enough that they are closed and bounded with respect, once again, to the usual distance. Okay, so the distance d prime that I defined in the counterexample is not the usual distance. Okay, it's topologically equivalent to the usual distance, but it's not the usual distance. Okay, so this concludes this video and section 3.3. Thank you for your attention, and in the next video we are going to cover section 3.4.